Right, thank you. The reason my sound isn't working so well. Okay, I think it's better now. So thank you again. So it's the second lecture. Initially, I was planning this to go first, but it's using a little bit of the ingredients I introduced yesterday. So what I'll talk about today is the quantum GIT conjecture, which is works. An application of the mirror picture of three-dimensional gauge theory, which I introduced yesterday, to Gromov-Witten theory of GIT quotients, and specifically for compact Fano manifolds. We'll see how that condition comes in. So the setup will be that X is a compact symplectic manifold. It carries action of a compact group by Hamiltonian symplectomorphism. So mu is the moment map, and the symplectic quotient is the inverse image of 0 under the moment map divided by the compact group G. I call it GIT as in geometric invariant theory because in the Kähler case, it is also the GIT quotient by famous result of Francis Kirwan. And the model statement, which has been known, I think, or conjectured, however you want to say it in physics, for quite some time, is that the gauge Gromov-Witten theory of X is meant to be the same as the Gromov-Witten theory of the GIT quotient X mod mod G when X is Fano and the quotient is smooth. Right. And a bit of history for that. So the Tori case was actually proved by Batirev. We may have to reinterpret the original formulas in terms of what we now call the Giventhal-Hori-Vafa description of mirror symmetry. As I mentioned, it was conjectured by physicists, maybe initially not with all the necessary condition. And today I'll present a recent proof with my collaborator and former student, Dan Pomerleano, for the quantum cohomology part of the Gromov-Witten theory. We hope that the method will get the entire Gromov-Witten theory. And this is based on a proposed proof I gave some years ago, and then I just somehow dropped the project. There were two problems with that proposal. There were two halves that didn't link very well. They link better now. And then in one of the halves had a mistake, and my collaborator's help was essential to correct that and do something that actually works. But one other reason why I didn't really pursue it as vigorously as I should have is the proof we have now is Floer theoretic. And in fact, there is, after staring for a long time, I don't see a path to an algebraic geometry proof, even if you assume that sorry, I need to move something on my own screen to see properly. A second. Sorry, I just had a little problem with my own screen here at home. Okay, that's better. Solved. So we're really using Floer theory and not algebraic geometry, even though when X is projective algebraic, you have a completely algebraic description both of quantum cohomology and of the GIT quotient. And what else I should add some background, some more objective background, not personal history, is that, well, what happens if you begin to loosen the assumptions and the statement progressively fails in that case? So if you drop the condition that the quotient is actually smooth, meaning that the G action is really free on the zero fiber of the moment map, then you still get a correct additive statement. So you will get an isomorphism between the gauge Gromov-Witten theory, the space of states for the gauged Gromov-Witten theory of X and the Gromov-Witten gauge theory of the quotient. But there are corrections to the quantum multiplication. And I don't know what's the first name I should put here. I want to put Iritani's name because he certainly studied Tori's examples of that early on. I couldn't swear if it's the first source. If you drop the Fano condition, then things begin to change more dramatically. Namely, cohomology of the GIT quotient becomes a bit too small, and it's only an additive summand in the gauged theory. And that was known from theoretical examples. And in physics, people say that the complementary part is the Landau-Ginzburg sector. Upon closer investigation, I failed to find a good meaning for that, because I'm going to give a mirror description in which everything is a Landau-Ginzburg sector. So I mean, you can say that the Landau-Ginzburg description contains a summand, which comes from the symplectic quotient, and the complementary summand, which is a bit mysterious, comes from some ghostly spaces that aren't there. All right, so everything in this page is great, except I didn't say what the gauge Gromov-Witten theory of X was. So in fact, as it is, I think this conjecture isn't even stated yet. So I need to state that. And for that, I have to remind you of the mirror description of gauge theory, which I had already introduced yesterday in a different context. And it involves the Toda space for G, which is also the Coulomb branch for cohomology, for pure gauge theory with a zero representation. And I'll probably draw a picture of a Toda space, but the key theorem that explains or encapsulates how this carries a mirror description of gauge theory is that if you take the space of states, if you take the space of states for an oriented local TQFT which has topological G symmetry and make it equivariant under G, so because if the theory has topological G symmetry, a space of states can be a coefficient system for equivariant cohomology. So take the equivariant version of that. Then the result is going to be a sheaf of algebras with Lagrangian support in the Toda space. Holomorphic Lagrangian support. And there are some assumptions secret here that I've put in a slightly concealed way. So first, I'm assuming not just that you have a well-defined DQFT with a G action, I'm assuming a G action is nice enough that the space of states is finite over the cohomology of BG, the equivariant space of states. So think of this being the quantum cohomology of a compact symplectic manifold by a famous theorem of Francis Kirwan that is a free modular finite rank over the cohomology of BG. The orientability is equivalent to the Calabi-Yau condition on the theory, and that implies an unobstructedness of certain deformations. And that actually tells you that this module over the Toda space can be quantized to a module of a non-commutative deformation, and that's forcing the support to be Lagrangian and finite. Now, a slight problem with this, I mean, you can write precise definition of what it means for a category to have these properties to conclude the theorem, but a slight problem with that is that in Floer theory or Gromov-Witten theory, the assumptions don't quite work, meaning it's not quite the case for general symplectic manifold. Even for Fanos, it's not known that you get a fully local TQFT from the Fukaya category of a symplectic manifold. In other words, that the space of states you compute as a Hochschild homology is really equal to the quantum cohomology. That is open in general. So you can't invoke the categorical constructions, but nevertheless, the conclusion is true, at least for compact symplectic manifolds of G action, that you do get an algebra over the functions on the Toda space. And here are some examples. So first, the flag varieties are some obvious symplectic G manifolds, compact symplectic G manifolds, even Fano. And they're leaves of what's called the Whittaker foliation of this Toda space. Toda space is an algebraic Lagrangian foliation. One presentation of the space is as a reduction of the cotangent bundle of mistake here of the Langlands dual group. Right. A reduction by the unipotent group on both sides. And in here, of course, you have the cotangent fibers, and they give rise to Lagrangian foliation, and that's the one. And these are the mirrors of flag varieties. So the calculation of the mirrors, I think at least for the maximal torus, was done by Reach, and then a long time ago I checked that this matched the leaves of the foliation. Another example, which isn't quite compact, but which relates to yesterday's talk. If you take, let's say, C star or S1, the compact group S1, and take its standard representation n times, then you do get so view it as a vector space, a symplectic manifold with Hamiltonian action, and you do get a Lagrangian z equals t to the n inside the cotangent bundle of C star, which is Laurent polynomials in Z and polynomials in tau, the compact. And what you notice about this is that something slightly funny happened. It goes to infinity in the wrong place because tau equals 0 is not allowed. So the projection to the base of a Toda system is not finite, meaning as a module over the cohomology of BS1 is in fact equivalent Laurent polynomials in tau. That's a feature of a non-compactness of the space you start out with. So what you get in here is actually not the quantum cohomology of the space, but in a non-compact setting you get the symplectic cohomology, if it works at all. So quantum cohomology goes with compactness of the space. And the Coulomb branch discussion actually is a way to address this. That was yesterday's talk, and I will not return to that today.
Sorry.
These are two examples.
Constantin?
Yes.
What's the reference for the fact that if you localize the equivariant quantum cohomology, you get the symplectic cohomology?
I don't think it's always true. It's only true in special cases. It's like in vector space. I know. You have a good chance when there's a normal crossing complement or something like that. There's some spectral sequences that relate symplectic cohomology with what happens in the divisor. But I don't think that's a general statement.
And are they known in the equivariant case?
In the vector space case, it's known because you can compute both. Even defining symplectic cohomology in the equivariant case, you have to be you need something to make it work well. You need some, I think they need a wrapping to dominate the moment map at infinity, because at that point, and maybe you might want the moment map to be proper for some statements. I'm not an expert on that at all. So I mean, I only studied a few examples.
Okay.
I'm afraid.
Thank you.
All right, so let's interpret a bit this story in terms of what it does for us, what it does for humanity. So the interpretation you want to think of is a character calculus for gauge theory, for three-dimensional gauge theory, or for boundary condition for three-dimensional gauge theory, or boundary condition for three-dimensional gauge theory are like topological categorical representations of the group, and surprisingly they have a rigid character calculus. Ordinary topological representation of the group, which are, you can formulate in different ways, but for example, the derived category of local systems over BG, the classifying space, does not admit a rigid character calculus, a soft kind of thing, meaning with extension classes and cohomological invariants. So funny enough, we can go up one dimension to three-dimensional gauge theory, its boundary conditions, which are categorical representations, you run into a rigid character calculus. That's known as mirror symmetry in this case. All right, so I'm drawing first, so ignore the very colorful stuff. Just look at black, greenish, okay. So black, greenish, and orange. Oh, orange is here. And let's make it disappear. All right. So this is in the Toda space for a group PSL2, and on the base I should have written or drawn some way the Toda base, which is spec of H star of BG, is down here, as the projection is down on the base, and it's a group scheme. It has a section, that's the unit section black here, and because I chose PSL2 and that has a pi 1 plus minus 1, there's a -1 section, so to speak. There's another one-dimensional categorical representation of PSL2 coming from the representation of pi 1. So there's another section in this case. Otherwise, this would be a bit nastier, the picture. And now what's happening here? So this is, oops. This is a point 0, I could have written it, the base point. And above the base point, you have what used to be the zero fiber in the cotangent bundle of the maximal torus. But when you pass from the maximal torus to a non-abelian group, what you have to do is blow up some points. And these are the exceptional divisors to blown up fibers. And you have to keep it affine, and you redo it by removing the zero fibers. An explicit recipe computing, telling you how you compute this. So you're missing this fiber. Instead, the fibers over zero consist of these two exceptional fibers. What else have I drawn here? I've drawn in red a special Lagrangian subvariety. It's given by the equation tau, the base coordinate tau, is q times z minus z inverse. The coordinate on the base is tau squared. So this is actually Weyl invariant in that both sides change sign of the Weyl group. So this graph is Weyl invariant. So it is a well-defined variety here. And these, for various q, are the mirrors of P1 viewed equivariantly for PSU2, PSL2, I think, or P1. So there's a whole foliation by these guys. Yeah, just drew one of them. Now here's in blue is a general gauge theory with G symmetry. So that can be gauged, and this is the support of its equivariant state of space in blue. And what I want to point out is this really bright pink intersection with the unit section. And these represent the spaces of states for the gauged theory. So it's Hom, it's a space of states going from Hom over G of the trivial representation for G to whatever the theory was. So once you have the, let's say, the space of states in blue, then intersecting with the unit section gives a space of states for the gauge theory. So that's a definition you could take. Definition by mirror symmetry, once you know the mirror. All right, and the theorem, now we can state it, is, that's what then is, if X is compact Fano with smooth quotient, then the quantum cohomology of the quotient is exactly this intersection, which I've written algebraically. It's the tensor product over these functions on the toda space with the function of the unit section of the original equivariant cohomology. A special case when G is actually a torus, then think that forget about the orange guys. Here you have a C star, and here these are fibers of C star, is that you intersection with the unit line is a fiber over the projection to the dual torus, and the functions on that are the Seidel operators set to 1. So in that case, the formula becomes take the equivariant torus cohomology and set the Seidel operator to some fixed value. Actually, 1 is the basis. You have to be careful when you want to change that. And that is secretly Batyrev's recipe for toric varieties. That's probably not exactly how he wrote it, but when you spell out what that means, you get Batyrev's presentation for cohomology of toric Fano varieties. And I've set them to be 1 here, but you could actually perturb the unit section a little bit. You have to, there's a Fano restriction on the linearizations. You have to be careful with that. So as long as you stay there, you can perturb it a bit. And the non-abelian case, you can also perturb a bit. So instead of taking the unit section, you could take one of these leaves of the foliation, but as long as it's so close enough that the reduction keeps you in the Fano case, you get the Fano quotient. Start with Fano, end with Fano. And as I said, the proof that we know goes by Floer theory, and we have no clue how to go by algebraic geometry to prove this. Maybe it's possible with difficult calculations, but there's no intuition that would allow us to get to that. All right, so I'll explain the outline of a proof, and so far as I understand it, if I get it really wrong, I'll probably get some hate mail from my collaborator tomorrow. But I hope I did not say anything that's outrageously wrong. So the first step to convert to something we can use is have to rewrite the tensor product a bit more topologically. And here's how you do it. So over the group manifold G, you can form a coefficient system. So at each group element, you can place the Floer homology of X with respect to the symplectomorphism G. That's a completely defined canonical space. It's of course isomorphic to the Floer homology of X itself, but not canonically so. So what you get is a derived flat connection over G, which you can identify nearby points, but involves the choice of path. So you get derived local system by the Floer continuation maps. There is also G equivariant, the whole thing for conjugation. So at any individual point is naturally equivariant for the centralizer of G, so the centralizer jumps. It's also multiplicative for the Pontryagin product on the group, and equivariantly even it's E2 multiplicative. It's because you can draw the multiplication in Floer homology as a pair of pans, and on the pair of pans you can now have a flat G bundle with given monodromies at the ends and still define the product, the Floer, so by solving the Floer equation along that. So that makes it E2 multiplicative. And finally, we're getting to what we want. The fiber over the point 1, which is the original Floer homology of X, carries a monodromy representation of omega G, because you had a flat connection on this system. If you make the fiber, take the equivariant fiber, you get the equivariant monodromy representation. So the equivariant Floer homology becomes an algebra over the equivariant homology of omega G inside the functions on the Toda space. So this, and the theorem is, this becomes the action of the Toda space on quantum cohomology. In fact, that's how you can, that's one perfectly valid definition of that action. I haven't defined another action yet, so I don't have to prove anything that agrees with something else. In principle, you can define another action by algebraic geometry methods, and I actually don't know a source for a proof that you get the same thing, but everyone I asked believes it. But since the application is done in Floer theory, this is the definition that we have to use. All right, and now finally the interpretation of the tensor product we're after on the right. So this gauge theory I had written before algebraically is actually a total cohomology over the group equivariant for G of this coefficient system with the Pontryagin product. That's a space of state. So now, even though I started with a mirror picture, I now managed to move away from that to something completely geometric in terms of X and G. And from here on, you can forget the mirror picture. But that's where the formula comes from. Any questions before I continue? All right, so now I'll outline the steps of a proof. So first, for the additive structure, for the multiplication, we don't have a very good argument yet. We think we have a valid argument, but not as nice. So we have to relate somehow the equivariant cohomology of X to the cohomology of the quotient. Now, there is a classical connection due to Francis Kerr in terms of a Morse theory of the square norm of a moment map, but that's kind of involves cycles and is local on the space. Floer homology, quantum cohomology is not local, so we have to make a change to that. And the change is actually obvious. Instead of thinking of just Morse theory, we do Floer Morse theory and take mu squared very seriously as a Hamiltonian, make it very, very big instead of keeping it small. Keeping it very small is just Morse theory. So make K very, very large. And what happens, you're going to begin to get lots and lots of periodic orbits in the part of X that lives near the zero value of the moment map. And in fact, the first theorem is that in the Fano case, I should have written that at the beginning. In the Fano case, it's not true otherwise. Every equivariant class, Floer homology class, flows eventually into a periodic orbit inside the Guillemin-Sternberg normal neighborhood of the inverse symmetry of zero under the moment map. That's essentially a T star G bundle over mu inverse of zero over G over the symplectic quotient. So everything comes in to live near mu inverse of zero. And that's where the Fano condition is being used. And in some ways, not very difficult, at least in some situation, because the more stratification tells you where to look for cohomology classes on X, and near all fixed points, you can actually check by a local calculation the cohomology flows out. So, I mean, yes, that it's kind of getting exhausted. But in the Fano case, you need more to actually to convert it to a proof. You need some global estimate of what goes where, when. And there is one. And because in the Fano case, you can define an invariant for each Floer class, the monotone index, and that will control the flow globally. What's being exploited as the ambiguity in the grading, in the Floer grading, if you don't add powers of Q, if you don't pass to the universal cover of a loop space, is the same as the ambiguity in the action function, the Morse function. And from those you can define some quantity which controls where and how quickly the orbits go. And there's a bit of a downside with this procedure that it's less obvious what happens in the non-Fano case. Well, in the non-Fano case, again, the local calculation will show that some cohomology sometimes gets trapped. The Hamiltonian mu square does not make classes flow out of fixed points. Some stay. This has to do with the signs of the weights on the normal bundle. And this accounts for the physics Landau-Ginzburg summand. So what would really need, I think, to make progress here, I still work in progress optimistically, what we need is a more combinatorial description, a non-Fano case of what part of the cohomology gets trapped. So I think that's not quite so easy. And one difficulty, I think, I don't want to spend too much time on this, but one difficulty is for local calculations that in general, the Morse function mu squared is not Morse bot. There could be singularities all over the place, and then local calculations don't work so well anymore. You have to start perturbing it to be able to do Floer calculations. All right, so what we learn is that you can bring all the cohomology near the zero fiber of the moment map, and there you have a chance of comparing it with a quotient. And, oops, I think the more efficient way to do this. So part B is that once we have the flow, we can define a lattice in the equivariant cohomology of X. So this is the ground ring a priori is polynomials, Laurent polynomials in Q, that's the variable you bring in to fix the Floer grading. And in there, I want the Z of Q lattice. And that was one place where it's important to get some help from some expertise, because in my original proposal, I thought, well, surely there's an obvious lattice in here. It's just positive powers of Q times classical cohomology classes, but that's not going to work for the proof. So what you have to do, and makes sense in hindsight, is look at where classes go when they flow and then when they're near mu inverse of 0, and declare the geometric classes there have degree 0. Geometric classes there of degree 0 and higher give you the lattice. So you don't cut off by the powers of Q in the quantum cohomology originally. Basically, you cut off by positive powers of Q once you brought classes in near mu inverse of 0, and very close, so it's almost flat, sort of in the normal directions, because that's where you want the magic to happen. And what this buys you, this is the important lemma, is that once you do that, with respect to this lattice system of lattices given by powers of Q on this cutoff, the Floer differential is going to have a topological part plus something that's positive powers of Q. And second, the Q power filtration is bounded in each degree. And this follows from a priori estimates relating the action with the area, the first one, and second follows from some bounds on degree and the Fano condition. And what do I mean by topological? Why do we even want to have something topological? Well, space of orbits that sit over a point in the symplectic quotient are generally a product of a copy of G times flag varieties of G. They're closed geodesics in G. And the topological, you have the group G acting on that, which is going to cancel the free factor of G. So there's a topological differential from the cohomology, a covariant cohomology of G with coefficients in this, that gets you the cohomology of G mod T. So that's what I mean by it has a topological part. And that one we want to keep. But anything that's Fleur, we want to throw away because we don't control it topologically. And now what happens with this? So let's ignore the Fleur part of the differential, the positive part, keep the topological differential, and see what happens to this global homology over the group of the family of Fleur homologies. Well, what happens when you move? Initially, over the identity, the Fleur orbits are closed geodesics in the group, but as you then move the broken loop, so you get all geodesics in the group. Well, what are all the geodesics in the group? They're a copy of G times a copy of the Lie algebra, which is a vector, the log of the geodesic after you plot it at 1. So now, if you take the G equivariant cohomology of this, you kill the G little Lie algebra is contractible, and you get the base. So by using the filtration now and breaking off the Fleur part of a differential, you can now see that the intersection becomes the homology of the base. Of course, what we've constructed is because we ignored some of the differential, we didn't construct an actual map. We construct a map from the associated graded of the quantum cohomology to the classical homology of the base. All right, so now, and that's why I said it's just the additive story. All right, so we describe an associated grade of the map from the gauge theory space to quantum cohomology, to actual classical cohomology of GIT quotient. Actually, what I described was the E1 term of a spectral sequence, but already the answer has the correct size. It's not going to get any smaller, so we're done, in fact. The actual map will have quantum corrections on top of it. So one of our goals going forward will be to see if we can describe the corrections, so that it would be useful to know that. We know how to do it in principle, we know how to define it, not to compute it necessarily, but define it, from a Lagrangian correspondence that relates the space X and its GIT quotient, namely the inverse image of the moment maps it mapping to the product. And in the Fano case, Lagrangian correspondence were discussed in this setting by Verham and Woodward. They were then generalized by Foucault in the equivariant case. So this actually has been well studied. And now, because again, it's geometric and very canonical, you can just combine that with a family over the group, Fleur family over the group for X. So one side of the correspondence is now going to be the Fleur family with the moving Fleur homologies. The other side is a constant family. And you get a correspondence bimodule between the quotient and the homology, global homology of the Fleur family. And that correspondence actually is additively isomorphic to both sides. So in fact, it gives an isomorphism of full quantum cohomology structures. And you want to think in the background, because it comes from geometry, it works at chain level. So all the finer structure is reflected there, like E2 structure of quantum cohomology. Now, so that's roughly end of the proof. So clearly what we would like to do going forward from here is find some description of the map. It's slightly unpleasant that everything was happening in closed string theory, closed Fleur theory. And now at the last place to introduce the fine structure, we still have to appeal to Lagrangian correspondences. So it'd be nice to be able to write the map in Fleur theory alone. And the general expectation is that one will end up with a version of Woodward's quantum Kerman map, I think, from equivariant cohomology of G. In other words, if you specialize the map we build to the equivariant quantum cohomology, you should get the quantum Kerman map. And another thing we'll need to look at going forward is, well, we think we can get everything we want from quantum cohomology. Does this work for all genus surfaces and for the Gromov-Witten theory? I'd like to say yes, But on the gauge side, in fact, I don't have a complete understanding how you build a higher genus theory out of the mirror picture. So that's still to be done. Okay, I'd like to conclude and probably be finishing just a tad early by showing this in a P1 example. The caution is, of course, there's nothing special about P1 manifold, except I can draw it. A manifold of circle action will work pretty much in the same way. The higher rank is what makes it a bit more difficult. The circle case is pretty simple, straightforward. All right, so let's start with P1. Let's start with the picture first. So P1 is here, or the sphere, the height function, z minus 1 to 1, and we're looking at the Hamiltonian, which is, I guess, 1/2 times the square of the moment map. And the periodic orbit will be at points k over n when, oh, I think I got this backwards. It's n over k. Sorry about that. Don't know what k over n over k, where n ranges from 0 to k. So there's the equator all the time, which are the constant orbits, actually. And then there are orbits of increasing winding number as you go up because of the value of the Hamiltonian, which keeps increasing. All right, so these are a space of, there's a circle's worth of periodic orbits for each circle. So this is a case of, what do we want to call it, Morse-Bott-Fleur theory. And it's better to keep it that way. Not try to perturb to regularize it. All right, so what's the natural labeling of the orbits for the Fleur complex? So what happens, well, you see what happens when you increase k, the orbits sort of move down towards the equator. So the orbits in the upper hemisphere come from the top, from the North Pole, the ones in the lower hemisphere from the South Pole. So the natural geometric thing to do would be to track where they're coming from. For each orbit, I'm going to write the complex in cohomology somehow. I don't know why. So I'm going to call Pn the Poincaré dual class of the point. Each orbit each orbit comes in a circle's worth of orbits, so space the circle. So by Pn, I'll call the Poincaré dual class of a point. It would have topological degree 1, but it would have Fleur degree 2n. It comes from the 2nth power of the equivariant variable sitting at the North Pole. And then there's a Poincaré dual of the circle, which has geometric degree 2, 0, but also Fleur degree 2n coming from the top. And the Fleur differential looks like this. So the boundary of Pn is, there's going to be a connection to the nearby orbit, the upper orbit, and the Fleur differential that connects it will go over the top. Then there's going to be a Fleur differential connecting it to the lower nearby orbit. That differential will want to have degree 2, but of course you have a class of degree 1, a class of degree 0, so there is a differential left. It doesn't disappear. And finally, there's a topological differential if you make things equivariant, which connects just Pn with Sn when you view it equivariantly for a circular rotation action. So this is the topological part I should have written. It's topological. And there's a lack of symmetry if you go down as to where why is the degree of Q here, first of all? Why is the power of Q here? Well, because the other differential goes over the South Pole, and when we're tracking degrees, we're thinking that everything came from the North Pole. So by passing over the South Pole, you've changed the labeling, and you've changed it by 2c1 of P1, which is 4, so you need a degree 4 correction here, Q squared. And there's a lack of symmetry here because on the bottom half, the orbits come from the bottom. So the Q squared is in the wrong place. And that is not, as you can see, is not a good description of the complex for our purposes. So the correct description of the complex is to normalize the things that have geometrically degree 0 in the part that we're computing. So define pi n to be q to the minus absolute value of npn, sigma n q to the minus absolute value of nsn, bring them degree 0. Oops, and that was for positive n. I see another mistake. Anyway, actually n0 is also okay. Otherwise, you have to change the sign of n in the lower hemisphere. So correct by the degree, so that the Poincaré dual of a point always has degree 1. The Poincaré dual of a circle always have degree 0. And when you do that, the differential takes the form you want. It's a topological part plus q times the Floer part. And the lattice consists of the non-negative powers of q acting on pi n and sigma n. So if you think geometrically where things came from, this Pn came from some, I think, u to the n power, maybe u to the n minus 1 power, tau to the n power at North Pole. And what we said, no, we want q to the minus n Pn in there. So actually, in terms of the classical cohomology, you're including some negative powers of q times classical homology classes in your positive quote-unquote part in order to get the differential to split up into the topological part and the Floer part. So that's an essential point. Oops. Here I did something wrong on this page. So let's see what we compute from here. So there's a Seidel operator going with a circle which acts. And it acts simply by shifting. It has degree 0 if normalized correctly. So it acts by shifting these generators, pi into pi n plus 1, sigma into sigma n plus 1. Now, if you compute the classical differentials, if you ignore the Floer part, and then you fix the value of z as in the Batirev recipe, you get the z of tau module, which is just z of tau over tau. You're killing tau because of, where is the difference? Because of a topological differential. And you have the ground ring, of course, of Laurent polynomials or Laurent series in Q. And that is a correct computation of the classical cohomology of the JIT quotient as a module over the cohomology of BS1, the fact that you set tau to 0. But if you keep the quantum differential instead, and then compute the differential, resolve the differential, and then evaluate Z, what you get, you're going to lose the pi's, they don't survive, they're going to mod out by an ideal, so the differential does. And what you get can be described as a ring of polynomials in the equivariant variable, Laurent polynomials in the Seidel operator, Laurent polynomials in Q, modulo this relation, and then fixing the value of Z. And what do you recognize in this thing I should have circled from the beginning? This guy is the equivariant quantum cohomology of P1 living in the Toda space for S1. So this is, let me just write it in words. This is the equivariant QH star S1 of P1. With respect to the Toda parameters, tau on the base and Z on the circle. So that's a correct formulation. So now you find the intersection with the fixed value of Z. That's a reward that is a Batirev construction for the cohomology of the quotient. That's how it works. And that is the end of my talk. And to compensate from yesterday, I'm finishing 3 minutes early.
Questions?
So I just had a comment. So this category that you studied at the beginning of like G equivariant sheaves on the group.
Mm-hmm.
So I think that this thing is the same as like what Tudor was calling like the category of lines in the 3D A model. Or I think it ought to be like a Betty version of it. Because he would have said something like it was D modules on B of the loop group, or the free loop group. And then that's roughly G mod G.
So this is not a bundle of categories, so probably one dimension off from that construct, a bundle of complexes of vector spaces on the group.
Right. Ours should be bundles of vector spaces on G mod G should be the line operators, and the space of all the category of all such things.
The category of such thing would be a space of line. No, that I believe, yes, yeah. But I mean, this when G is finite, for example, this is the orbifold quantum cohomology. I mean, I think it leads to chain-around quantum cohomology. So, or I think I forgot what the original name for that was. Maybe even discrete torsion or something in the 90s physics literature. So finite groups, it's in the Floer theory. I think it's very old. So.
I see. Very cool.
Are there any other questions?
Is there any generalization over Fano? So think for a more general situation of X.
Right. So I made some very quick comments at the beginning. Where were they? Yes. So things begin to fail. Even if you start with the Fano manifold and you reduce, you need to choose a linearization of the action. So there's always a Fano linearization from the Chern class, from the canonical anti-canonical bundle. Even if you move the linearization, the theorem begins to fail, and it fails even additively then. So what happens is, we can explain this picture as if you try the same trick, the same flow, some cohomology gets trapped. The extreme case, of course, if you have a total sector, you can choose the value of the moment map that's out of the image and try to reduce there. And if all the cohomology will try to flow towards the end, the limit fixed points, but it won't escape, obviously. So you get something on the gauge side and nothing on the topological side. So whether there's a topological interpretation in terms of some other spaces you could build of the missing sectors, I think that's a good question, but I don't know. I don't know suggestions for that.
Any more questions? Okay. So let's thank the speaker again.
Thanks, everybody. And I regret again I wasn't able to come in person. I'm afraid it's the middle of term here. But, thank you
very much for those very well prepared talks and
thank you. So,
time an odd hour in your time zone.
right.